Hello, this is Mr. P, and today we're going to learn about the dot product of two vectors. When multiplying vectors, there's more than one way that you can multiply vectors. One way is the dot product, which is also known as a scalar product, and the other way would be the cross product, which is also known as the vector product. The dot product is referred to as a scalar product because the result of the operation is going to be a scalar, will be a number, whereas the cross product will produce another vector. Now, one thing that the textbooks are not good at is showing you the geometric interpretation of dot product, which I'm going to add here. This is not actually in your textbook, but I believe it is something worthwhile. Because with vectors, you definitely want to take a geometric approach to vectors, which will make you a better problem solver. So let's start out with two vectors. Let's say we have vector v and vector u. Well, if you're going to do the dot product, which is our two-dimensional multiplication, then it's very intuitive if the vectors are both in the same direction. If they're both pointing in the exact same direction, then the dot product, and this is how we would write v dot u, is going to simply be the product of the lengths of the two vectors. And we know that the length is the magnitude, so it will be the magnitude of v times the magnitude of u. And if they're both in the same direction, that's an easy way to do it. Now, if they're not in the same direction, that's when we have to get a little more creative. For example, let's say they were arranged like this. This is our vector v and our vector u, and they're not pointing in the same direction. So what we want to do here is take the idea from physics, and we're going to project vector u onto the line that includes vector v. So we're going to think of the line that contains vector v, which I've made here as a red dotted line, and we're going to project u onto that line. And you can think of it as if light rays were coming down perpendicular to our red line, then the projection would be the shadow that's cast upon that line. In other words, if you take the terminal point of u and drop a perpendicular to the line, then this distance here from the initial point here to the right angle, this side of the large triangle, that is going to be your projection. So if we think of this red line as a number line with the initial point being at 0, then the coordinate of this intersection, let's call it x, that would represent the distance of this side. So now, if I projected u onto the line that includes v, I projected u onto v, and now I have two lengths that are in the same direction. So now I can say that v dot u is simply going to be that magnitude of v, and then the magnitude of the other one, the magnitude of x, is just x itself. And then we have our dot product. Now, there was another way we could have done this. Instead of projecting u onto v, we could have projected v onto u. That would be the same idea. We're going to take the terminal point of v, we're projecting onto u, so we're dropping a perpendicular to u, which would look like that. And then this distance, that would be the shadow of it. Let's give that a variable. We're going to call it y. So now we have our two vectors, so to speak. One of them is actually a scalar, but we have our two lengths. So this time u dot v is going to be the magnitude of u, which we write like that, times the length of this side, which is y. Now the important thing is to realize that these two quantities are actually going to be equal to each other. It doesn't quite look like it intuitively, but they are going to be equal to each other because the commutative property does hold for the dot product. So v dot u is the same as u dot v. But of course, let's prove that. I want you to consider the angle between these two vectors. Let's call that angle theta. Then if we compare the small right triangle to the large right triangle, we'll notice that first of all, they're both right triangles. And then this angle theta is actually in both of the triangles. So by the angle-angle postulate, these two triangles are similar. which means their sides are going to be in proportion. So we're going to set up a proportion. And looking at the large triangle first, I'm going to say the hypotenuse of the large triangle, which is the magnitude of u, is to the short side of the large triangle, which is x, as the hypotenuse of the small triangle, which is magnitude of v, is to the short side of the small triangle, which is y. So setting up that proportion, we can do a little cross multiplication, and we see that the magnitude of v times x is equal to the magnitude of u times y, which means these two quantities are the same, and therefore the commutative property does hold with dot product. Now, a couple of observations can be made here regarding the dot product. First of all, notice how if theta is an acute angle, if it is less than 90 degrees, then when we have the projection come down, the projection is going to be in the same direction as our other vector. So if we think of that projection as another vector itself, then both vectors are going to be in the same direction. So it doesn't matter if they're both in a positive direction or both in a negative direction. Negative times a negative is a positive, or positive times positive is a positive. That dot product is going to be a positive number. So if your dot product is positive, then your theta is going to be positive. Is going to be acute. Now let's say we take a look at the vector u. If I start to move vector u, and just for a little comparison here, if I start to move vector u this way, in other words, I'm opening up theta, then this perpendicular starts to move with it as well. Or in other words, point x starts to move towards the initial point. And as I keep going, a larger and larger angle of theta makes x smaller and smaller until I reach the point where I am perpendicular to the line which contains vector v. At that point, the projection will project down to a point and will have no length. It will be a zero vector itself. So therefore, the product is going to be 0, which tells you that anytime the dot product results in 0, the two vectors must be perpendicular. And then if I continue opening up that angle into an obtuse angle, then when I drop my perpendicular, it'll be on the other side, which means I'll have one vector going one way, one vector going the other way, so that product is going to be negative. So this is something that we're going to see later on in the notes, but if your dot product is positive, your angle is going to be acute, that is the angle between them. If your dot product is 0, then the two vectors are perpendicular, and if your dot product is negative, then your angle is going to be obtuse. And speaking of that angle, let's look at one other thing. If we were to think trigonometrically now, we want to think of x being this side of the triangle, the base of this large right triangle. Then I can say x is equal to the hypotenuse times the cosine of the angle. If you remember, the opposite side in a triangle is the hypotenuse times the sine of the angle, and the adjacent side is the hypotenuse, which is magnitude of u, times the cosine of the angle, which is theta. And from this we can imply, so this implies by way of substitution into this equation, I want to take this equation and instead of x, I'm going to substitute this expression. And that will give me the fact that the dot product of v dot u is equal to the product of the magnitudes times the cosine of the included angle. So now we can get back to our original intuitive idea of dot product, which is simply the product of the magnitudes. And that works great if they're in the same direction, but if they're not in the same direction, then it's simply the product of the magnitudes times the cosine of the angle between them. Now, luckily, we don't have to keep doing the magnitudes every time. There is a algebraic shortcut way to calculate the dot product. So along with this geometric understanding, let's look at the algebraic definition. And the dot product is defined as the product of the vertical components plus the product of the horizontal components. Or in other words, if vector v is a1i plus b1j, and w is a2i plus b2j, then a1 times a2 plus b1 times b2, when you add them together, that will be the dot product. So let's see a couple examples here. We're given these two vectors, v and w, and we're first going to do v dot w, means I'm multiplying 2 times 5, and I'm multiplying negative 3 times positive 3. And when I do that, I get 10 and negative 9. Combine those, and I get a positive 1. Now for the second one, they're asking for w dot v, which we already know geometrically is going to be the same answer as a, but we'll check the numbers anyway. This time it's 5 times 2 plus 3 times negative 3, which of course is 10 minus 9, which is 1 again. Also, we have v dot v means v dot itself. So I'm going to take 2 times 2 times 2, and then negative 3 times negative 3, and that's going to give me 13. It'll be 4, and positive 9 is 13. Likewise, w dot w is going to be 5 squared and 3 squared. So 5 times 5 plus 3 times 3 is 25 plus 9 is 34. And then from the last section, we're finding the magnitudes. We have magnitude of v is going to be the square of the first one, square of the second one, add them together and take the square root. And that, of course, gives you the square root of 13. Likewise, magnitude of w, we're going to square 5 to get 25, square 3 to get 9, add them together, get 34, and take the square root. Now, if you notice C and E, you have 13 and square root of 13. And D and F, you have 34 and square root of 34. That is not a coincidence. And if you think about it logically, v dot v means vector v. If you think of vector v and then times itself, let's say you have two of the same exact vectors. If you're comparing it with itself, of course it's in the same direction, which means it's just multiplying the two magnitudes together. So v dot v is simply going to be the magnitude of v times the magnitude of v, which is the magnitude of v squared. So the magnitude of v is square root of 13, square it, you get 13. That should make sense to you geometrically. All right, we're also going to look at some properties. We've already seen the geometric reason for the commutative property upholding, but the distributive property also works. You can say u dot this sum means you can distribute it to be u dot v plus u dot w. And then we just mentioned this property that v dot v, or any vector dot itself, is simply its magnitude squared. And the 0 vector times any vector using dot product is going to be 0. Remember that the result of a dot product is a scalar. That's why this 0, which is in bold, is the 0 vector, and this 0 is just the scalar 0, the number 0. All right, next we want to talk about angles between vectors. And when we're talking about the angles, of course, here's our formula, which we've really already derived, because if I take this denominator and put it over on this side, then I would have the simple fact that the dot product is the product of the magnitudes times the cosine of theta, which we saw in that first slide. So solve that for cosine, and you get this formula. But when we talk about the angle between two vectors, let's say we have these two vectors. If they're not crossing, then the angle between the vectors is the same as the angle between the two lines that contain the vectors. So you can either extend the lines that contain them, which would give you this angle here, Or, since we're talking about vectors, another way to do it is you could move the vectors so that they share a common starting point, and then the initial points are the same, so the angle between them would also be theta. And of course, we can see here two parallel lines cut by a transversal. The corresponding angles are congruent. So there's two different ways to look at that. But to reiterate some of the observations we've seen before, let's say we plug in our numbers here. We do the dot product, we find the magnitudes, and put them all into the formula. Then what we're going to see is a couple of situations that could come up. First of all, you could have cosine theta equals 0. And that would happen only if theta itself is a 90-degree angle, because the cosine of pi over 2 is 0. So that would happen only if your two vectors are orthogonal. And orthogonal just means that they meet at right angles. It means the same as perpendicular. The other special situations you can see is if the cosine of theta is 1, after you replace all the values here and simplify it, if you get cosine theta equals 1, that means that the angle would have to be 0. Theta would have to be a 0-degree angle, which means your two vectors are parallel, but in the same direction. And the other situation that could happen is cosine could be -1, which would also mean that they're parallel, but this time they're in opposite directions. So the possibilities for theta go from -1 to 1, and those are the extremes we see in the range of possibility for theta. Theta could be anywhere from 0 to pi, so 0 to 180 degrees if you're in degrees. And theta is 180 degrees if cosine is -1, theta is 0 if cosine is 1. And then halfway between those is the other special case where they are orthogonal, which gives you cosines equal to 0. Also notice that in order for the right-hand side of this equation to be 0, that can only occur if the numerator is 0. The denominator can't be 0 because you can't divide by 0. That would be undefined. So if the numerator is 0, then you'll have cosine theta equals 0, which is orthogonal. And we're going to see down the road a little bit that that is our test for whether two vectors are orthogonal. All right, so let's look at a book example here. The book wants to find the angle between these two vectors. And your first step, we'll just follow along with their work. The first step is to compute these three quantities. You want u dot v, the magnitude of u, and the magnitude of v. By the way, in textbooks, they typically make vectors boldface. But when you do them in your own writing, when you're doing them by hand, you do need to put the arrow on top because you can't distinguish between the bold and not bold in handwriting. So don't get sloppy on your notation. Make sure you have the arrows above them. Anyway, if we do the dot product, which after a little time you should be able to do them in your head, basically, you're going to get the dot product is -7. The magnitude is going to be square both numbers, add them together, and then take the square root. But if you notice 3 and 4, you might recognize that this is simply a triangle with sides 3 and 4, which makes a 3, 4, 5 triangle. So you should have really already known that that magnitude was going to be 5. And for the magnitude of v, it's 2 squared plus 5 squared is 29, and then the square root of that is square root of 29. Once you have those three values, you simply put them into the equation. So they have cosine theta equals this quantity. And this is where the book does something that I recommend you do not do. It puts this into the calculator and gets an approximation of -0.26. I highly recommend against doing that because ultimately we want theta. So you're going to take the arc cosine of both sides, and when you put it in the calculator, I would put it as arc cosine of this exact quantity, not arc cosine of this approximate quantity. So you never want to round in the middle of the problem like they just did. But if you do it correctly, you should find that theta is approximately 105 degrees if you round to the nearest degree. Now, speaking of the calculator, there's one other thing I want to show about the calculator. So we're going to do one more of these. And this time we want to find the angle between these two vectors. It's 3, 4, and 2, -1. And we're first going to start out with the quantities u dot v. So the dot product between the two would be 3 times 2 is 6, and then 4 times -1 is -4. Add them together, you get a positive 2. Magnitude of u, hopefully you recognize the 3, 4, 5 triangle. If not, it's 3 squared plus 4 squared, then take the square root. Magnitude of v is going to be 2 squared plus -1 squared. Add them together, take the square root, you get square root of 5. And then this is going to be the equation we use. Cosine of theta is the dot product over the product of the magnitudes. So cosine of theta is 2 over 5 root 5. Now, this is where I see a common mistake happen over and over and over, putting this incorrectly into the calculator. Of course, we're going to take the arc cosine of both sides, the inverse cosine of both sides. So when we put it into the calculator, I want the inverse cosine of this quantity. However, you have to realize the difference between the division bar that we write and use all the time and the button on the calculator that is the division operation. The division bar is a grouping symbol, but when you press the division button on the calculator, it is just an operation. And in order of operations, multiplication and division are the same order of operation. So let's look at two different ways to put it in the calculator. The common way I see that is absolutely wrong would be to put it in just like it looks, is the inverse cosine of 2 divided by 5 root 5, and then closing the parenthesis for inverse cosine. But that gives you 26.56, etc. And that is the wrong answer. Because to put this in properly, you have to treat the entire denominator with the grouping symbol. So you have to put an extra parenthesis around it. So the correct way to put that in would be 2 divided by, and then open a parenthesis, 5 root 5, close the parenthesis, and then you can close the parenthesis for your inverse cosine. And when you do it correct, you'll find that theta is approximately 80 degrees. That is, if your calculator is in degree mode. So just be very careful of that little trap when using the calculator. Alright, and one other way that vectors are very useful is they are a very quick way to find out whether or not two vectors are orthogonal. And two vectors are orthogonal if and only if their dot product is 0. And the if and only if means if their dot product is 0, they're orthogonal. And if they're orthogonal, then their dot product is 0. And by the way, just as far as terminology, I do want you to be aware that orthogonal, perpendicular, and normal are all terms that mean meet at a right angle. The difference is in the usage, where you're going to use orthogonal when you're referring to two vectors. You're going to use perpendicular when you're referring to two lines. And you're going to use normal when you're talking about either a line and a plane or a vector and a plane. And the other thing to realize is that the 0 vector itself is orthogonal to every vector. So let's look at the question, are these vectors orthogonal? Well, first of all, we have 3 times -10 is -30. And then 5 times 6 is a positive 30. And if I add those together, you see I do get 0. So the dot product of these two vectors is 0, so therefore, yes, they are orthogonal. I didn't even have to draw them out. I could just see by the dot product that they are orthogonal. Next we have these two vectors. 2 times -4 plus 3 times 3 would be -8 plus 9, which is 1, which is not 0. Doesn't matter whether it's positive, negative, just as long as it's not 0, then we can answer our question, no, they are not orthogonal. So these two vectors do not meet at a right angle. Alright, and we talked about projections before. Let's see the actual equation for that. I know it looks a little intimidating, but the idea here is the same as you you saw in physics when you try to find out how much of a force is applied in a certain direction. Those were projections as well. And here we're going to talk about the vector projection of v onto w. And another way to think of it is it's a decomposition of v into two different vectors. One of them being parallel to w, and the one that's parallel, that's the projection. And the other one is the one that's perpendicular to w. So in our diagram here, vector v is this one going up diagonally, and vector w is the one going along horizontally. Well, if we drop a perpendicular from the terminal point of v to the line that contains w, then this shadow, so to speak, if you had a light bulb on the top, this would be the shadow. If all the light rays were perpendicular to w, then this length here, this vector, is the projection, vector v1. And then this other vector is the one that would needed from the initial point. If you went the projection, that is the other vector that is needed to get to the terminal point. So that's what we mean by decomposing vector v into two different vectors, one of them being parallel and one of them being perpendicular to w. Now a little bit about the notation here. Some people get these two letters backwards. The idea here is we're projecting v onto w. So it's a projection of v. So when we think of an argument of a function, like for sine or cosine, you're taking the sine of the angle or cosine of the angle, and what you're taking it of, that's your argument. So here it's the projection of v onto w. That's why w is down where the base would be, and v is the argument. Some people see this and they read it backwards. They try to read it as the projection of w onto v from left to right, but that would not be correct. It's the projection of v onto w. And like we said, visually that is v1, and the formula for that is simply the dot product divided by the square of the magnitude, and then that is times the original w vector. Remember that dot product is a scalar, the magnitude is a scalar, so this is just going to be a ratio of how to resize w so that you have v1. Also notice that v2, which would be this vector, is going to equal v1 minus v minus v1. That's because v1 plus v2 equal v. And if we simply bring the v1 onto this side, you have v2 equals v minus v1. So once you find the projection, then simple vector addition and subtraction can find the other vector for you. All right, let's look at an example. We're asked to decompose vector v into v1 and v2, where v1 is parallel to w and v2 is orthogonal to w. Okay, these are our two vectors. And let's look at this geometrically first so you see the situation we have here. If we look at the two vectors, and these are pretty much drawn to scale, notice how vector v is negative 3, positive 2. So from the initial point, we go negative 3, positive 2, and I put both vectors in standard position. So negative 3, positive 2 would look approximately like that. And using the same scale, a positive 2, positive 1 would look approximately like that, positive 2, positive 1. So we want to find what is the projection of v onto w. So this is the line we want to project onto. So this is the terminal point that I'm dropping the perpendicular to. When I do that, it would look like this. This is the line that contains w, and we're projecting v onto w, so I'm dropping that perpendicular this way. Now v1, being the one that's parallel, that's going to be the actual projection, which is this vector right here. That vector is the projection, and the second vector we're looking for is the other side of the triangle. So to calculate this, we need two things in order to be able to calculate this. We first need the dot product, which is negative 3 times positive 2, plus 2 times positive 1. That gives us negative 6 and positive 2, which is a negative 4. We also need the magnitude of w. And this one is w, so it's simply 2 squared plus 1 squared gives us 5, and then you take the square root of 5. Then we're simply going to put that all into the equation we have. The dot product was negative 4. The magnitude squared, remember the magnitude was square root of 5, so if I square it, I get 5. And that is going to be multiplied by the original vector itself. So distribute that, and we're going to see v1 is negative 8/5 I hat minus 4/5 j hat. Now we could do some projections to try to find the v2, but the much easier way is just to recognize that v2 is simply v minus v1. So we have v is this vector here, but be careful of your algebra here. It's minus all of v1, so you do need to distribute that negative sign when you're combining like terms. But if you do that properly, you're going to find v2 is negative 7/5 I plus 14/5 j. Remember, in order to, looking at the first term, the negative 3 minus a negative 8/5, that's going to be negative 3 plus 8/5. But we need a common denominator, so 3 is the same as 15/5. So we have negative 15/5 plus 8/5 is negative 7/5. So make sure you're adept at working with the fractions. All right, and one final example, and we're just going to do it algebraically. I'm not going to draw the diagram for it. But it does show that sometimes you can get very different looking directions that are really asking for the same thing. This time they want you to find the projection of u onto v, and then write u as the sum of two orthogonal vectors, one of which is the projection of u onto v. And this is really the exact same directions as the last problem. So here are the two given vectors. We first need our dot product, which is negative 5 times negative 1 plus negative 1 times 1, which is 5 minus 1, which is 4. And then the magnitude of v would be negative 1 squared plus 1 squared. Take the square root, and you're getting at square root of 2. And using our formula for the projection of u onto v, and be careful of which one you're projecting onto which. If you're projecting onto v, that's the one you're going to be taking the magnitude of. So u1 is the projection of u onto v, which is the dot product over the magnitude squared and times the original vector v. And when we replace those numbers, we get 4 over the square root of 2 squared, which is 2, and multiply through, you're going to get negative 2 comma 2. So that is u1. And notice how this time we're using angle bracket notation rather than the hat notation. So to find u2, it's simply going to be u minus u1, which is our original u, and we're subtracting our answer we got in the first step. So here it's a matter of negative 5 minus a negative 2 is negative 3, and negative 1 minus 2 is negative 3. So therefore u, they want us to write it as a sum of two vectors. U is going to be negative 2 comma 2 plus negative 3 comma negative 3. And we're done.